All right, good morning. So on Monday, we started sort of discussing examples of integer programming problems. So remember, in integer programming, there were three assumptions that should be satisfied by an LP problem. So they were basically proportionality and additivity, divisibility, and the third one was certainty, basically. And then we said that, there are some examples in which proportionality and additivity is satisfied. Certainty is satisfied, but divisibility is not satisfied, right? So, and in such cases, we actually sort of formulate problems as an integer programming, or IP problems for short. And more recently, we started looking at so-called binary variables, and we sort of said that binary variables actually give us great flexibility in terms of modeling yes/no type decisions. So today we're going to continue our discussion. So this is known as the shortest path problem, and it's a very simple problem, as the name is quite self-explanatory. So essentially, think of the following situation. So suppose that we have the following figure. And then we have some arcs in between. So what kinds of things can be actually explained by such a picture? So transportation is a good example. So for example, you can think of 1, 2, 3, 4, 5, 6 as the cities or different towns, and you can think of the arcs as the roads. So for example, we can go from 1 to 3, you can go from 3 to 5, you can go back from 5 to 1, and so on and so forth. So that would be an example. Alternatively, you can view 1, 2, 3, 4, 5, 6 as airports, for example. Okay, so there are different airports, and the arcs actually represent direct flights. So for example, there's a direct flight from 1 to 3, there's a direct flight from 1 to 4, but there's no direct flight from 1 to 5, for instance. Okay, so to go to 5 from 1, you have to first go to 3, and then you have to continue on to 5. Okay, so basically, this is a special figure. So this is known as a directed graph. So there are two words here. There's the word directed and there's the word graph. So first of all, let me sort of start by defining what a graph is. A graph basically has two components. So N is a set of nodes, and A is a set of arcs. So nodes actually correspond to those sort of circles. So we have 6 of them in this picture. So we have 6 nodes. And the arcs correspond to those arrows, basically. So, for example, there's an arc from 1 to 3, there's an arc from 1 to 4, and so on and so forth. So where does the word directed come from? Well, directed comes from the fact that the arcs are directed in the sense that you can go from 1 to 4, but you cannot go back. Okay, so think of this as like one-way streets, basically. Okay, so you can only go from 1 to 4, but you cannot come back to 1, at least not using the same direction. Okay, not using the same arc. Okay? So as a result, the easiest way to think about this is, the arcs actually represent one-way streets. So you can only travel from 1 to 3, but you cannot go back 3 to 1, okay? Using the same road. That's what I'm trying to say. In this example, as I said, there are 6 nodes. So the set of nodes is given by 1, 2, 3, 4, 5, and 6. And we also have a set of arcs. So basically, there are different ways of representing this, but one of the most common ways is the following. So you actually denote an arc by the endpoints. So there's an arc from 1 to 3. Okay. Then there's an arc from, let's say, 1 to 2. Then there's an arc from 1 to 4. Then there's an arc from 2 to 1. And you can actually write them down, okay? So in this case, I guess 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 arcs in this graph, okay? So one thing that you should pay attention to is the following. So the order is important, okay? So 1, 3 basically means that there's an arc starting at 1 and going to 3, okay? And 1, 2, and 2, 1 are different from one another. Okay? 1, 2 is the arc that goes from 1 to 2, and 2, 1 is the arc that goes from 2 to 1. Okay? So, as a result, whenever you look at these sort of pairs, basically the first one is the origin node, and the second one is destination node in some sense. Okay? So, another way to think about this is, for example, there is a direct flight from 1 to 3, or there's a direct flight from 1 to 2, 1 to 4, 2 to 1, and so on and so forth. Okay? Is that clear? All right, so what are we trying to do? Well, we have certain parameters of the problem. So I'm going to denote by Cij. So Cij is cost of arc ij. So what do I mean by this? So for example, if you view this as a transportation network, okay, so you can think of Cij as the length of the road. Okay, so for example, C12 is the sort of length of the road from 1 to 2. Okay, similarly, C24 is the length of the road from 2 to 4, so in kilometers or whatever. For example, if this is a sort of flight network, then you can think of C12 as the cost of flying from 1 to 2, and C24 is the cost of flying from 2 to 4, and so on and so forth. So depending on your application, you know, Cij's actually may have different meanings. So Cij can correspond to cost or time or distance and so on and so forth. Okay? So as a result, in general, I'm going to just sort of say that there's a certain cost which you have to pay associated with each arc. And I'm going to define this for every arc in my graph. So for every arc, there's going to be a cost. So C12 is the cost of traveling from 1 to 2. C21 is the cost of traveling from 2 to 1. C24 is the cost of traveling from 2 to 4, and so on and so forth. Okay? Of course, we assume that the costs are non-negative usually. Okay? All right, so what are we trying to do? Well, our goal is the following. So find a path of minimum total cost from node 1 to node 6. So essentially, right now I'm at node 1. So think of 1 as Ankara, for instance. Okay? And think of 6 as, for example, New York. And what I want to do is I want to fly from Ankara to New York. And I want to do this using the sort of smallest fare flight, so to speak, the cheapest flight or cheapest flights. Okay? So what kind of a route should I follow so that I'm going to end up in New York with the smallest amount of total cost? Okay? So as I said, I mean, you can view the nodes as the airports. So for example, 2 can be Istanbul and 3 can be, let's say, Paris and so on and so forth. And what you want to do is you want to go from 1 to 6 and you want to pay the smallest total amount of cost, basically, okay? So you want to incur the smallest total amount of cost. And the question is basically, how can we formulate this problem as an optimization problem? Okay? So first of all, is the problem clear? So as I said, I mean, this is known as a directed graph. And the reason why it's called directed is because each arc has a direction. Okay? There are also some other types of graphs in which the arcs are not directed. So then we call them undirected graphs. But this one is a directed graph because each arc has a direction, which means that, you know, each arc starts at a node and ends up at a different node, basically. Okay? And as I mentioned, in this graph, there are 6 nodes and there are 11 arcs, I think. Yes. Okay? So the question basically is the following. So how can I formulate this problem as an optimization problem, okay? So to do that, again, we need to first decide our decision variables, figure out what they are. And once again, you know, one thing that you have to pay attention to is the following. So Cijs are given to me, okay? So Cijs are not variables. I know Cijs beforehand, basically. So, for example, I know the cost of flying from Ankara to Istanbul. I know the cost of flying from Istanbul to New York, and so on and so forth. So somebody already gave me these costs, and based on these costs, I want to figure out the cheapest flight from Ankara to New York. Okay? All right, so what are the decision variables? So what can I control in this problem? Okay. The nodes visited might be a decision variable because that depends on my choice. What else? Alternatively, instead of nodes, what can I look? I can look at arcs, basically, right? So which arcs am I going to use, basically, right? So for example, you know, if you think of these as flights, each arc corresponds to a direct flight from, you know, a node to another node. So which of these flights am I going to take? Okay, so which flights will I take to go from 1 to 6? And if you think about this a little bit, so basically, for example, that essentially means the following. For each flight, such as the one from 4 to 6, I'm going to make the following decision. Should I fly from 4 to 6 or not, basically, right? So what kind of a decision is that? Well, this is a yes-no type of decision, basically, right? Should I take that flight or not? Okay. So what kind of variable do we define for such decisions? Binary variables, exactly. So as a result, what I'm going to do is the following. I'm going to define xij, and I'm going to set it equal to 1 if arc ij is on the shortest path from node 1 to node 6. So what does that mean? So basically that means that in going from 1 to 6, am I going to use this arc or not? Am I going to use this flight or not? Okay? And it's going to be 0 otherwise. Okay? So how many decision variables will I define? Well, there will be a decision variable for each of the arcs, basically, right? Okay, so as a result, these will be defined for every arc ij in my graph. And for this particular example, there's going to be 11 decision variables, basically, because there are 11 arcs. So let me ask you a different question. Why is this a binary variable instead of, for example, an integer variable? So why should I consider each flight exactly once?
Because we have to minimize the cost, so we don't want to choose 1 to 2 and 2 to 1. Because it's the same for us.
But my question is the following. So basically, can it happen that, you know, I'm going to take the same flight more than once in the optimal solution? No. Why not? So think of the following situation, okay? So for example, I'm flying from 1 to 2, okay? Forget about that. So think of the following example. So I'm going from 1 to, let's say, 4. Then I'm, forget that again. So let me give you another example. So let's say I'm going from 1 to 3, okay? 3 to 5. And then I'm coming back to 1 again, for instance, okay? Then I'm going from 1 to 3, 3 to 4, 4 to 6. Okay? So this would be a solution where I'm going to take this flight more than once, basically, right? But I claim that that cannot be the optimal solution. Why not? Well, because, you know, the first time I arrived at 3, I could have actually followed to 4 in the first place, right? So there's no point in actually going from 5 and back to 1 and taking this flight again. Okay? So in other words, taking the same flight more than once does not give me anything in terms of smaller cost. Okay? So as a result, for each flight, I'm going to consider it exactly once. So should I take this flight or not, basically? Does everybody see that? Okay? All right, so now let's try to figure out our model. So first of all, I'm going to write down the general model. So we're going to try to formulate it as an IP problem because we have binary variables. This cannot be an LP problem. My goal is to minimize my total cost. So how can I express my total cost? So this is going to be a minimization problem because I'm interested in minimizing total cost. Okay? So the question basically is the following. How can I express my total cost in terms of xij's? Well, let's figure out what the sort of contribution contribution to costs are. So basically, if I fly from 1 to 6, I'm going to look at individual flights, basically, and I'm going to add them up, right? So, for example, if I use the flight from 1 to 3, then I'm going to pay C13, basically, right? And if I don't use the flight from 1 to 3, then I'm going to pay nothing. Okay?
A
Exactly. So if I multiply Cij by Xij, now let's figure out sort of what this expression is. If Xij is equal to 1, so that means that I'm using the flight from I to j, then I'm going to pay Cij. Okay? And if Xij is 0, that means that I'm not going to fly from I to j, then I'm going to pay nothing because I'm multiplying them. Okay? So as a result, this expression will be either Cij or will be equal to 0. Okay? Depending on whether I use it or not. So this is the contribution of arc ij to my total cost. Okay? So what's my total cost? So I'm gonna sum over what? Well, I'm going to sum over each individual arc, basically, right? So I'm going to look at all ij's in my arc set, and among all of them, I'm going to actually sort of consider these expressions, Cij times Xij, and I'm going to add them up. So basically, this expression means that I'm going to look at all ij's in my arc set A. Okay, so for example, in the example, A will be equal to 1, 3, 1, 2, 1, 4, 2, 1, and so on and so forth. Okay, so once again, this is a shorthand notation to indicate that I'm going to pick my ij's from the set capital A. Is that clear? Okay, so you may not have seen this before, but this is sort of common notation. So this tells you where you're going to pick your ij's from. Okay, so you're going to pick your ij's from your arc set. Okay, and for example, in that example, A consists of 11 elements, so there's going to be 11 terms actually in the summation. Okay, in some other graph, there may be 20 arcs, then you're going to have 20 terms, and so on and so forth. So, but this is a general objective function, so this is true for any directed graph. Okay, so of course, based on the directed graph, number of terms may be different, but you still use the same notation, basically. Okay, so that's important. Is that clear? So this is the total cost. All right. So now, what are my constraints? Now, let's think about this a little bit. So right now, I'm at node 1, and this is where I want to go, basically, right? So which means that the fact that I'm here right now, and I want to end up in this node, actually brings some constraints, okay? What kind of constraints does it bring? So basically, I cannot choose my flights arbitrarily, okay? So I have to follow a certain logical order, basically. And let me start with the original node. So right now I'm at node 1, and I have to get out of node 1, basically, right? So this is my starting point. So which means that at node 1, I have to take one of these flights. I need to take either flight from 1 to 2, or 1 to 4, or 1 to 3. Why is that? Because right now I'm at this airport, and these are the only flights that I can take. Okay? So how can I write as a constraint?
When I is 1, it cannot be 0.
What cannot be 0?
6, because we must start with 1, and we must use it at first time.
Okay.
And we have to, at the end, we have to use j as 6, and this also cannot be 0. In x, I, j, we set it.
Okay, but how can I write this as a constraint?
J, I, j1j, x1j, it must be equal to 1, and ji6 and xi6 must be also equal to 1.
What do you mean by x1j? So,
Türkçe anlatayım.
okay.
Yani x 1 ile başlayacağız nasıl olsa. O yüzden i'nin 1 olduğu bir tane olmak zorunda. O yüzden o da 1 olmak, yani 1, yani 0 veya 1 ya, hani, ya da 1 değil de en azından x 1, j 1 olmak zorunda. 6 ile de bitireceğiz, o yüzden i 6'da hani 1 olmak zorunda, x i 6.
But my question basically is the following: how can I write as a constraint in terms of xij's? So xij's are my decision variables. X1j must be equal to 1, but for which j?
İşte hangisi olursa, yani ne olursa olsun. Değil mi?
Well, how else can I express this?
We should choose the minimum cost, I think. Started with the first point, so we can write this C1j times x1j minimum.
So you're saying that I'm at node 1, and I'm going to look at these flights from node 1, right? And among them, I'm going to pick the one which is the cheapest.
Yes.
Is that necessarily true?
Great algorithm, I don't know.
Well, I can have a situation such as this one, right? So the cost of flying from 1 to 2 is 1. The cost of flying from 2 to 3 is 3, let's say. But the cost of flying from 1 to 3 might be 2. Right? If I want to go to 3, then I should pick this one, actually. Okay? All right. Any other suggestions?
Maybe x12 plus x14 and x13 should be greater or equal to 1.
Okay, so now we're sort of heading in the right direction. So basically, now, right now I'm at node 1, okay? And I should definitely take one of these flights leaving node 1, because I have no other choice, right? Otherwise I'm stuck, basically. So what does that mean? So I have to either pick the flight from 1 to 3, or I have to pick the flight from 1 to 4, or I have to pick the flight from 1 to 2, okay? And since I don't want to come back to 1 again, okay, I should pick exactly one of these flights, basically, right? So once I leave the first airport, I don't want to come back, basically, because coming back to the airport 1 does not help me at all. Okay? So what does that mean? So there are 3 choices that I have, so which is from 1 to 2, 1 to 4, and 1 to 3. And among these, I should pick exactly one of them. Why exactly one of them? Because, as I said, you know, I should definitely get out of here, so I should pick at least one of them. And I don't want to come back to 1, so that means I have to pick exactly one of them. Okay? So the question is, how can I write this as a constraint? Well, I'm going to look at all flights leaving 1, okay? And I'm going to look at the corresponding variables xij. I'm going to sum them up, and I'm going to set it equal to 1. Okay? So how can I write it as a constraint? Well, so again, here's a shorthand notation. So I'm going to look at x1j's. So the first index will be 1, and the second index will be j. But I'm not going to look at all j's. I'm going to only look at j's such that there's a flight from 1 to j. Okay? So in this example, j can be only 2, 3, and 4, for instance. Okay? So how can I express it in general? So here is, again, you may have seen this notation for the first time. So I'm going to look at values of j such that, okay, there's an arc from 1 to j. So this notation, again, is important. So that basically tells you the following. So I'm going to look at values of j such that, so that column basically means such that, okay? I'm going to look at values of j such that there's an arc from 1 to j, okay? So for example, in my example, j can be 2, 3, or 4. But j cannot be equal to 5, for instance. Okay? Why not? Because there's no flight from 1 to 5. Okay? So I'm going to sum this up. And this summation is nothing but the number of flights I'm going to take from airport 1. Okay? How many flights am I going to take overall? And obviously that number should be exactly equal to 1. Okay? So this means that I should take exactly 1 flight from node 1. Okay? To get out of node 1. Does everybody understand this notation? So once again, this basically means that I'm going to look at nodes j such that there's an arc from 1 to j. Okay? So I'm going to look at all direct flights that I can take from node 1, basically. All right? So this makes sure that I will definitely leave the first town or the first airport. Okay? So now let me focus on the destination. Okay? I want to end up at node 6, basically, right? Okay? And I can come to node 6 only from airport 4 or airport 5. Okay? So these are the only incoming flights. Okay? And this is my destination. Well, if this is my destination, then I should either come from here or from here, basically, right? I have no other choice. So how can I write this as a constraint? Well, if you think about this a little bit, so that sort of pushes me either to take this flight or this flight. Okay? So this is now the opposite of node 1. At node 1, I have to take 1 flight out of node 1. At node 6, I have to take 1 flight into node 6. Okay? Exactly. So let me write it over here. So now I'm going to look at the following. So now I'm going to fix the second index at 6. And the first index can take different values. Okay? But I'm going to actually restrict I to the following. I'm not going to look at all i's, but I'm going to look at which i's? I'm going to look at those i's from which there is a direct flight to node 6. Okay? How can I write this as an expression? So I'm going to look at I such that I, comma 6 is an arc. So for example, in this example, I can be 4 or I can be 5. Because I only have an arc from 4 to 6 and 5 to 6, but nothing else. Okay? And this summation should be equal to 1 as well. So the first one tells you that you should take exactly one flight out of node 1. And the second one tells you that you should take exactly one flight into node 6. Okay? And then this is quite intuitive, right? So you have to leave the first airport and you have to get into the last airport. So as a result, you have these constraints. Do we need anything else? Well, so if I just leave my problem as this, formulation as this, then I may run into the following problem. So for example, my model can take me from 1 to 3. Okay? Then my model can take me from, let's say, 5 to 6. Well, the problem is, how am I going to get from 3 to 5? I have to do something about that, right? Okay? So in other words, I have to make sure that I have a continuous path from 1 to 6. So far we don't have that yet. So far we just guarantee that from node 1 I will definitely get out, and I will definitely get into node 6, but in between I don't know what to do now. Okay? So the question basically is the following: how can I fix that? Now here is one way to think about this. So for example, in this example, if I go from 1 to 3, okay, so now I'm at airport 3. Well, I don't want to get stuck at airport 3. So if I'm coming into airport 3, then I should also get out of airport 3 as well. Okay? So basically, if I end up at airport 3, then I should definitely either take this flight or this flight. Okay? So how can I write this as a constraint? Okay? Okay. Let me give you a more general sort of argument. So suppose that this is airport I. Okay? And at airport I, there are some incoming flights. Okay? And there are some outgoing flights. Okay? Now, in my optimal solution, I may or may not visit airport I. So that I don't know. Okay? So for example, if that's my solution, then I'm visiting airport 3, but I'm not visiting airport 2, for instance. Okay? Now, there are two cases then. So I may either end up visiting airport I, or I may just bypass airport I. So I may not visit at all. Okay? So let's think about the first situation. If I visit airport I, then I should definitely take one of these flights. For example, this one right here. Right? Because there are only 3 flights coming into airport I, and I should have taken one of them to end up at airport I. Okay? Well, if I come to airport I, then I should definitely leave airport I, so I should either take this flight or this flight. Okay? So maybe I can take this flight. So this is the first scenario, right? So if I visit airport I, then if I'm coming into airport I should also get out of airport I. So here I is all the airports that are different from 1 and 6. So I'm looking at intermediate airports, basically, okay? What's the second situation? The second situation is the following. So I may not visit airport I at all. Okay? And if I don't visit airport I, then obviously I cannot take a flight from airport I either. Okay? Now what does this suggest us? So, well, in the first case, if I look at the number of flights coming into I, in the first situation I'm taking exactly one of them. And if I take exactly one of them, then I should also take exactly one of these flights. Okay? In the second situation, if I'm not taking any of these flights, if the sum of flights I'm taking is equal to 0, then sum of flights I'm taking here should also be 0. Well, how can I generalize this? Number of incoming flights should be the same as number of outgoing flights. Okay? In other words, the number of incoming flights I'm taking should be exactly the same as the number of outgoing flights I'm going to take. Okay? If it's 0, then this should be 0 as well. If this is 1, this should be 1 as well. Does everybody see that? So the question is the following. How can I write as a constraint now? Well, there are two types of arcs that I need to consider. So I'm looking at node I. So first I'm going to look at nodes that go into node I, or nodes that have arcs that go into node I. Okay? And I'm going to write as follows. So I'm going to look at all nodes k such that there's an arc from k to I. And I'm going to write xki. So what is this expression? So this is the total number of flights I'm taking into node I, basically. Okay? So from this, I'm going to subtract the number of flights I'm taking out of node I. How can I write it as a constraint, as an expression? So I'm going to now write xij. Okay? But now j can be only the nodes from which there's an arc from I to j. So in other words, I'm using k to represent nodes here, and I'm using j to represent nodes over there. Okay? And what's this expression? What's this difference? That should be equal to 0, exactly. Okay? And I'm going to write this for all I such that I can be equal to 2, 3, 4, and 5. So for each of the other nodes, basically, I'm going to have one such constraint. Okay? So now, this guarantees that, if I come into node I will also get out of node I. And if I don't come into node I, then I cannot come out of node I either. Okay? And finally, of course, we have the fact that xij is a binary variable. And I want this to be true for all ij's. Well, so once again, if you look at this constraint, this is exactly like a balanced constraint, basically, right? So whatever comes in should be the same as whatever comes out. Okay? So this is pretty much like the inventory problem that we looked at. So whatever comes into the system is the same as whatever comes out of the system. Okay? So here our system is node I, basically. So number of flights coming into node I should be the same as number of flights leaving node I. Okay? So again, this is like, these are known as flow balance constraints. Okay? So you balance the flow. So the incoming flow should be the same as outgoing flow, basically. Does everybody see that? So, any questions? Yes?
Why don't you write in constraints to make sure that you don't visit, for example, 3 to 1?
Okay, that's a good question. So the question basically is the following. So why don't we add the constraint that, for example, we can visit each node either once or never? Right? That's the question. Okay? So essentially, for example, why don't I have an additional constraint that says that I can come into node 3 at most once? Okay? Well, the reason is the following, because if I have a solution in which I'm visiting node 3 more than once, okay, then I can shortcut my solution again. Okay? And by shortcutting my solution, I can actually decrease my cost. Okay? So in other words, the optimal solution will never visit any node more than once.
And why didn't you write the first two constraints? Because they would say to be one anyway.
Well, okay, so why did I write these two constraints? Because I want to make sure that I'm going to take a flight from node 1, and I want to make sure that I'm going to take a flight into node 6. Okay? So essentially, think of this in the following way. At node 1, I should definitely take a flight out of node 1. And at node 6, I should definitely take a take a flight into node 6. Okay? For every other node, I may either visit or may not visit the node. Okay? So the other constraints basically tell me, the last sort of 4 constraints, I from 2 to 5, actually tell me that if I visit a particular node, then I should also get out of that node. And if I don't visit a node, then I cannot get out of that node either. Okay? So I may never have a situation where, for example, I come from 1 to 3, and then I go from 4 to 6. Okay? Why not? Because if I'm coming into node 3, then I should either go here or here. Okay? Other questions? So once again, is this notation clear? So this is important because we're going to be using this over and over again. Yes?
Bigger than 0 instead of 1, right?
You mean here? So you're saying this? Well, we cannot have strict inequality, right? So we should have greater than or equal to, or less than or equal to, or equal to. Okay, so we don't allow this type of constraint. And you can have more than 1, or greater than or equal to 1, but that in the optimal solution, again, that will be equal to 1. Because there's no point in coming back to a node that you already visited, okay, in the optimal solution.
What around 6, you don't need to write equal to 1. It can be bigger or equal to 1.
Yes, so I agree with you, but what I'm saying is that in the optimal solution, it will necessarily be equal to 1. Okay, so as a result, by writing 1, we don't lose anything. By writing equality, we don't lose anything. Okay? Other questions? All right, so basically, if I solve this problem, then I can figure out the shortest way to go from, or the cheapest way to go from 1 to 6. And, you know, whichever xij's are equal to 1, they correspond to flights that I'm going to take, okay, on this path. And once again, please pay attention to the fact that the constraints make sure that you have a continuous path, a connected path, basically, okay? So you start from a node, you start from 1, you go to 3, and if you come to 3, then you go to 4, then from 4, you can go to 6. So as a result, you have a connected path. Yes?
You said that we have the CIJs, but what do we have as CIJ value for those nodes that are not connected? For example, C16.
Oh, C16 basically, I'm defining these costs only for the existing arcs, right? So since 16 is not an arc, there's no C16 basically in my formulation, and there's no X16 in my formulation either, right?
So we will never have a solution that says we will go direct from 1 to 6.
We cannot in this situation because there's no arc from 1 to 6. Okay? So I'm defining my variables for each arc. And if there's no arc, then there's no such variable, basically, right? Okay? Yes?
I'm saying what I understand so that it can be clear for me. For example, let's say we go 1 to 2,
Mm-hmm.
and our solution says maybe we can go 2 to 1 again,
Mm-hmm.
but in the optimal solution, still there is no such kind of thing. We can say this model is okay.
Okay, so let's think about it. So the question basically is the following. What if my sort of model actually takes me from 1 to 6, takes me from 1 to 2, okay? And then I come back to 1, right? So that's the question.
But we cannot connect from 2 6 because we say that from 1 to another node we have to choose one of them.
Exactly. So now think of this constraint here, right? So this constraint tells me that I should definitely use one of the flights that goes into 6. So for example, I use such a flight. Okay? Well, if I use such a flight, then I should definitely come into node 4 at some point. Okay? So for example, such as this one. And if I come into node 3, then I should definitely go into node 3. Well, then there's a problem here because at 1, I'm taking 2 flights. I'm taking this one and this one. Okay? So as a result, essentially now I'm actually violating this constraint. Okay? So these constraints actually ensure that I have a connected path that starts from 1 that goes all the way to 6. Okay? So essentially, if I have only this constraint, then you're right. But by having these constraints as well as these ones, I make sure that everything should be connected.
You say first one provides we just get out of first airport. Second one we can land to the sixth one, and the other one it just makes the connection between the lines.
Exactly, yes, exactly. Okay? That's a good question. Other questions? So let me just tell you another version of this problem then. So this is a slightly sort of more general version of the problem. So this is 16b. So how can we find all the cheapest flights flights from node 1 to every other node, solving a single optimization problem. So now the question is the following. In the first version, so we only wanted to go from 1 to 6. So now we want to go from not only 1 to 6, but we want to go from 1 to every other node. And we want to do this using the cheapest possible flight. Okay? Of course, what you can do is the following. So you can solve this problem for every node. So you can solve this for 6, 5, 4, 3, 2, and 1. 6, 5, 4, 3, and 2, basically. But then in a case, you're going to be solving 5 different problems, right? So my question is the following. Can I solve a single problem and make sure that I can find all the cheapest flights from 1 to every other node? So now I'm interested in flying from Ankara to Istanbul with the cheapest flight, to Paris with the cheapest flight, to London with the cheapest flight, and so on and so forth. So, and I want to figure this out solving a single problem. Okay? So what would be different from this formulation now? Well, we do actually, right? So we have different landing points, more precisely, right?
Like X was the landing point, and we put maybe X rather than 6 in the previous problem.
Well, here is one way to think about this. So in the first problem, we wanted to go from 1 to 6, and we said that we should definitely take a flight from 1, and then we should definitely take a flight into 6, and then in between we should have connections, basically, right? Okay. So now try to think of it in the following way. So, for example, the cheapest flight from 1 to 6 may be this way right here. Okay. The cheapest flight from 1 to 2 may be this one right here. The cheapest flight from 1 to 4 may be this one right here. And the cheapest flight from 1 to 5 may be this one and this one right here, for instance. Okay? In the previous version, we actually asked ourselves the following question. Are we going to take that flight or not? And that sort of gave rise to these binary variables, right? Okay? So now, can I think of this problem in the following way? So how many times am I going to take this flight in the optimal solution? So for example, I may take this flight to get here as soon as possible. I may take the same flight to get here as soon as possible. I may take the same flight to get here as soon as possible. Then I may take this flight to get here as soon as possible, and so on and so forth. Okay? So now instead of taking each flight exactly once, I'm going to allow myself to take flights more than once. Okay? So I'm going to define my decision variables in the following way. So xij is no longer a binary variable, but this is number of times arc ij will be used. In an optimal solution. And I'm going to define this for every arc ij. Okay? And I will try to sort of write my model accordingly. So once again, my total cost will be the following. So I'm going to multiply Cij by Xij, because Xij is the number of times I'm going to take that flight. Okay? And I'm going to sum this over all Ij in my arc set. So now what are my constraints? Well, let's try to think of it in the following way. So how many times will I be leaving airport 1? Well, I'm going to be leaving airport 1 once to get to 2, once to get to 3, once to get to 4, once to get to 5, and once to get to 6, basically, right? So how many flights will I take from 1? So I should take exactly 5, but I'm going to only look at j such that there's an arc from 1 to j. So this number now will be equal to 5. If you think about this a little bit, this is just an extension of the previous formulation, right? In the previous one, we were taking only 1 flight. So now I'm actually leaving airport 1 5 times, 1 for each of the other nodes, basically. Okay? All right, so what about the other nodes? Well, I'm going to have the same situation, basically. So I'm going to look at node I. There's a bunch of incoming flights. And there's a bunch of outgoing flights, right? But now there's one difference between the previous problem. So in the previous problem, we said that if I is an intermediate node, then if I come into I, then I should leave I. And if I don't come into I, then I'm not going to leave I. Okay? So now there's a difference because each of the remaining nodes will be a destination. Okay? For some flight. So what does that mean? So it means that, for example, number of times I'm coming into node I should be 1 more than number of times I'm leaving node I. Okay? In other words, if I'm visiting this node I 5 times, for instance, okay? Among those 5 times, 1 of them will be my destination, okay? And 4 of them should continue to the rest, okay? So how can I write this as a constraint? Well, by the same reasoning, so think of the nodes here as k, and think of the label them here as j. So I'm going to look at all k such that there's an arc from k to I. I'm going to look at xki. So this is number of times I'm coming into node I, basically. Okay. From this, I'm going to subtract number of times I'm leaving node I. So j such that ij is an arc. I'm going to look at xij. So number of times I'm coming into node I minus number of times I'm leaving node I should be equal to 1, exactly. Why is that? Because every time, I will be my destination for 1 flight. Okay? So as a result, if I come here 3 times, for instance, then only 2 should leave. Okay? Because for 1 trip, this is already my destination, my last point. And I'm going to have this for which nodes? I can be equal to 2, 3, 4, 5, and 6 as well. Okay? So now 6 is no different from other nodes. Okay? So as a result, now essentially what I'm doing is the following. I'm going to leave node 1 exactly 5 times. And I'm going to leave 1 flight at every node, basically. Okay? So at every node, I'm going to stay once and continue my other destinations. So number of times I'm visiting that node I minus number of times I'm leaving node I will be exactly equal to 1. Okay? Another way to think about this is the following. So suppose that I'm actually sending trucks, for example, from node 1 to every other node. Okay, from node 1, 5 trucks will come out. Okay, and at every other node, exactly 1 truck will stay. Okay, so number of incoming trucks minus number of outgoing trucks is exactly equal to 1. So if there are 4 trucks coming into node I, 1 of them will stay here and 3 of them will continue. Okay, so by solving this problem, I'm going to figure out all the shortest paths from node 1 to every other node. Okay, what else do I need? Of course, xij should be non-negative for all arc ij. Anything else? Well, xij denotes number of times I'm going to use that arc, so that should be an integer. So as a result, xij should be integer value. So if I solve this problem, then I'm going to be able to figure out all shortest paths from node 1 to every other node. Okay? So by solving a single problem, I can compute all the shortest paths. Yes?
What if we had, let's say, 100 nodes? Because the solution will say us that we are using nodes by node 40, let's say, 60 times. But how are we going to organize the solution in order to make the shortest paths?
So here, of course, I'm assuming that I'm writing this model based on that graph. Okay? So if I have 100 variables, of course, now this is going to be equal to 99. Okay? So the right-hand side of this will be 1 less than the number of nodes, basically. Okay? So if I have 100 nodes instead of 6, then number of times I'm going to leave this will be equal to 99, basically. And minus 1, exactly, yes.
But the decision variable says the number of times the arc is used, but how do we know that the arc is used? Because the solution will give us, I don't know, just the cost, but how are you going to know that the arc is used for to go to 4 or to
Oh, okay. Now I understand the question. Okay, so basically you're saying that if I solve this problem, then I'm going to end up with, for example, x1, 2 will be equal to 3, x2, 3 will be equal to 5, and so on and so forth. How could I figure out the optimal solution? Is that your question? I see. Yes, that's not too hard to do, because essentially what I'm going to do is, at each node, I'm going to figure out the number of nodes coming in, and I'm going to figure out the, which arcs are sort of being used to get out, and then the difference will tell me one path that comes into node I. Okay? So, for example, if I use this node twice, and then if I use this node once, then what do I know? Well, I'm going to go from 1 to 4, for instance. So I'm going to take this flight. And to go to 6, I'm going to take this flight plus this flight. Okay? So that's essentially how I'm computing it, right? So I'm going to take this flight to go to 4. That's going to be the cheapest flight. And to go to 6, I'm going to take this plus this one. Okay? So I'm going to basically just sort of piece them together, so to speak. Okay? Other questions? I'll see you next time.